Hi, Dr. Tran.
Hey Chris, how's it going?
It's going all right. How about yourself?
I'm good. Yeah, good to be back.
That's good. Glad to hear that everyone's okay. Well,
Yeah,
good
thanks.
at least.
Yeah, I think she got me sick a little bit, so I'm feeling a little bit of a cold, but
Hmm.
um, I think it's not what she had. So I think she had like some kind of like bronchitis or something like that.
Oh,
So I mean, she was coughing really bad. So
yeah.
I just have a fever, a little bit of fever. So
Hmm.
not so bad for me, but
Yeah. I hope she gets better.
thanks.
Uh, I got a quick question in regards to the homework.
Sure.
I'm sure you've been asked this several times, but I'm having that issue with FEA where I'm getting an error when I'm doing the solids,
Uh-huh.
and not really sure how to figure that out or solve it.
What's the error message?
Let me go ahead and solve it. Oh, that's weird. For some reason, it won't solve. That's really weird.
It's just not solving at all.
It won't give me the option to solve. I was able to do it yesterday, and it gave me an error. But
Oh, okay.
yeah.
So for the solid element analysis, if you're able to get a simulation off with that, then that's great. But it's also but I also know that a lot of people are probably not going to be able to get it off, which is the point, right? And so the whole point is that with the challenging geometry like this, like it's going to work a lot better with shells and beams. And so if you're not able to get it done with the solid elements, then then just don't worry about it. And so for the activity submission, you can just say that I tried everything I could and I kept running into errors, and I just wasn't able to get this to work. So some people I think have been getting it to work just through just with tinkering with it. I was able to do it on my computer too, but the whole point was so that this geometry is just a lot more difficult to do with solid elements. So if you're not
Okay.
able to do it, then that's fine.
Okay. Should I also include that for the summarizing my findings? That
Yes,
like I can't really compare it because of the error.
sure.
So
Yes. Yep.
okay. All right. Perfect. Thank you.
Mhm.
Hey, Dr. Trenton, how you doing?
I'm good. How are you?
Can't complain.
How was your weekend? You just spend it recovering or anything? Good?
Yeah, just mostly just sleeping and recovering.
Mm.
I was feeling sick at the end of last week, and then yeah, I just tried to sleep as much as I could for the weekend.
Yeah, that's good.
Professor, question for you.
Yep, sure. What's up?
For the answers, I've been trying to make a moment in it,
Mhm.
and so far I haven't been able to create a like moment like about the X or the Z. It like only allows me to create about like the Y depending on the orientation of the object. Is there a way for me to do a moment like about the Z and the X?
Yeah. So you can just like we do for forces and pressures, you can change the defined by instead of I think it's vector. I think you can change it to components, and then when you
Okay.
change it to components, you can individually set the moments in whatever direction that you want.
Okay, thank you.
Yep. Yeah. Remember, for moments, the when you set the direction, that's the axis of rotation, and so it's going to create a moment around that.
Okay. So then, like, let's say if I have a moment about the x-axis, in order to do the component, just have the force in the x, or no, or about the y.
So you can supply a moment boundary condition itself. And so one of the boundary conditions you can actually supply, we haven't used it in an activity yet, but instead of like a force boundary condition or a pressure boundary condition, you can supply a straight up moment. And then the moment you would specify the axis of rotation for the direction.
Okay. All right. Thank you.
Sorry, so same question about the subject he just was mentioning. So
Mhm.
it's like if it's like a moment, so moments is like around the axis of rotation. So
Yeah.
basically it's just this way for like the upper side and then this way for the like a downward side. Maybe it's just like, we have to like, do you have to separate it, or it's just like it's just automatically like that? If you just like put a magnitude there and it just automatically assumes like we just like
Yeah, so you just place a magnitude and then you specify which direction you're rotating, and then it basically it applies like a twist on that entire surface.
got it. Thanks.
Do you know if we'll ever go over the thermal stuff?
Probably at the very end. Yeah.
Okay.
What would be the difference between using a force versus a pressure?
So you can get the same thing with both. It's kind of just personal preference on what's kind of easier for you. I would say for most cases, force is going to be more convenient because I think we think of things in terms of like weight and how much force it's going to be.
But would that affect, then we'd have to determine where we're like to the
Exactly. Yeah.
Okay.
And so if you have like a distributed force over a whole surface, then you can get the exact same thing with the force or pressure. It's just you just have to convert the units based on whatever the surface area of the object you're doing. But
Okay.
yeah, you can do both. Most of the time, force is going to be more convenient.
Okay.
Yeah.
Thank you.
Mhm. All right, it's 5:30, so let's go ahead and get started today. All right, a good evening, everyone. How's everyone doing today? I'm good, doing good. All right. We're in week 9. Oh, what's up?
Oh, I said we're good. We're good.
Good, good. Yeah, so we're week 9, so we're officially past the halfway point of the semester. So we're feels like we've done so much already, but then still so much left to go. Right. Okay, so the plan for today is we're going to be continuing on with our lecture notes of truss equations. So I think we kind of just barely started it last Thursday, and so this week we'll really get into it. Okay. Some announcements I want to make, and so I've pushed back the due date for activity 4. So right now activity 4 is supposed to be due, I think, tomorrow night, 11:59. But a few people have come to me and said that this week's kind of been just really crazy with a lot of other stuff, and so for me, because we're not going to be doing an ANSYS activity in a while, so I'm okay pushing the due date for that back, and so that's going to be due on Friday now, 11:59. Okay, so you guys have a couple extra days to do that. It is a little bit of a lengthy activity with a lot of steps to it, and so if you haven't started, definitely start it now. Even with the extended due date, I think it's going to take it takes a while to get everything working right for that one. So, but hopefully that gives you a little bit more breathing room for that. Okay. I've also gotten a couple of requests for the midterm project, excuse me, to push the due date back for that, and so I'm okay with that too. But I don't want to push it back too far, because then that's going to start pushing into kind of a lot of the other stuff we have planned for the rest of the semester. But so right now the midterm project is supposed to be due next Friday at 11:59, and so I can go ahead and push that back. So they have one more weekend to work on it. I can go ahead and push that back until, let's say, following Tuesday at 11:59. So hopefully that gives you an extra weekend and a couple extra days to work on that. Okay. But I don't want to push it past that, just because kind of a couple weeks after that we're gonna have our midterm exam, and then you're gonna start working on your final project after that too. Okay. But I can at least give you a couple more days for those things. Okay. So I need to change that in Canvas. So I haven't had a chance to do that on Canvas yet, because it's kind of been a busy week for me as well. So after the lecture today, I'm gonna go ahead and update the due dates for those, just so that it reflects on Canvas. Okay. All right. One more announcement I want to make, which is indirectly tied to the midterm project, but this weekend, starting on Friday, I'm going to be unavailable until Sunday night. I'll be going out of town to Columbus, Ohio, actually, and so a good friend of mine is getting married out there. So I'll be flying out on Friday, basically spending half the day on the plane, and then sleeping as soon as I get there. Saturday is the wedding, and then Sunday I'm coming back. And so if you have questions on the project, you can feel free to email me, of course, but don't expect a response until Sunday night, maybe, but probably Monday morning is probably more accurate, because I think probably after coming back I'll be pretty wiped out. Thank you. Yeah. And so kind of take that into account as you're kind of planning ahead for the project. Okay. All right. And so I think that's all the announcements that I have. I don't have the next homework assignment ready for you guys, but I think I'll have that ready probably by Thursday, and that's going to be covering a lot of the stuff we're covering now. And so, like the finite element theory stuff, direct stiffness, truss equations, and then eventually beam equations as well. And then I think I'll probably give you guys about 2 weeks to work on that too. Okay. All right, and so I think that's it for the announcements. And so are there any questions I can answer? Yeah.
Just to be sure, this Friday the activity, and then November 2nd the project.
Is November 2nd, is that the Tuesday after?
Yeah.
Okay, yeah. So this Friday, which I believe this Friday the 22nd, and so Friday the 22nd for activity 4, and then Tuesday November 2nd for the midterm project. Yeah.
Thank you.
Yep. Mm-hmm. Right. Any other questions? Yep.
It's kind of off topic. Do you have a date on when you get married?
No, I do not. We're
I'm talking about all your friends getting married.
I'm of that age, yeah. So I'm and I talk about this to my friends all the time, that a lot of our friends are kind of getting married, and kind of one right after the other. But we're planning on buying a house first, and then we'll probably think about wedding after that, because a lot of the venues that we're looking at, they're kind of booked for 2 years already anyway, and so so might as well look at a house first, and then we'll think about that after. But yeah, probably not going to happen for that. We'll probably do a courthouse wedding sometime after we buy a house. So yeah, that's our plan. Rent out a hangar. Yeah, actually, there's a lot of speaking of just really quickly. We're looking at houses in Chino, and apparently there's some rumors that they might close down Chino Airport and they might turn that whole area around the airport into new housing. So we were looking around that area, but Chino is really far from everything. So I don't know if I want to move up there.
I wouldn't be surprised. They're doing a lot of construction over there.
Oh yeah, yeah.
Like Eastvale area too.
Yeah, Eastvale, Chino. There's a lot of stuff going out there. So yeah, their houses are cheap, but it's just so far. I mean, the commute to work is okay for me, but for my family, it's going to be really far because my family lives kind of in West Orange County, so a little bit close to Long Beach, and so for them to come out all the way out there would be really far. So, but that's all life stuff. Life stuff is complicated. In some ways, life stuff is more complicated than engineering. I feel like engineering, at least, there's equations for that, and it'll give you the same answer no matter what. Okay. All right, any other questions before we get started? Okay, all right, so let's go ahead and talk about truss equations. All right, and so last week we were introduced to this idea of the direct stiffness method, right? And the reason we're going down this path is to kind of get an understanding and a little bit of appreciation for what's going on underneath the hood, right? And so kind of the highlights from the direct stiffness method that I want you to carry on, for this week and next week are kind of the overall process of solving a finite element problem by hand, right? And so there were a few steps that were involved here, right? And so the first step is to look at your geometry and look at all the elements and form the element stiffness matrix for each element. Okay. Step 2, so after you have all the element stiffness matrices for all the elements, is you're going to assemble them into a single global linear system. Once you have your global linear system, remember that's basically one big matrix set of equations that you can solve for all of the unknowns in the system. But before you solve it, you would have to apply boundary conditions. And we talked about how constraint type boundary conditions and load type boundary conditions, how they affect the linear system differently. Okay. Because without the boundary conditions, the linear system is unsolvable. Right. Step 4 is to actually solve. And remember, this part is usually done by a computer. And so we talked about how to set this up in MATLAB, or if you want to use just whatever other tool you feel most comfortable with, then go ahead and go for that. Okay. And then step 5 is you're done basically. And so step 5 is profit, I guess. I wrote the 5 and I didn't think about what to write for it. So, profit. All right. And so, this is the general process through which, that we're going to solve. Obviously, we're going to solve finite element problems by hand. But even complex codes like ANSYS, they kind of follow this general process as well, right? And so they have kind of all these major steps. It's just that how they do it is very different. Okay. And we walk through this entire process with spring elements, right? And so when we were doing step 1 right here, all the element stiffness matrices that we encountered use a spring constant to some degree. Okay. But what we'll see for the truss equations and then next week for the beam equations is that this step right here is going to be different depending on what type of element that you have. Okay. Okay. And so today we're going to be introducing a new element type called trusses. Okay. and you'll see that the truss has its own unique element stiffness matrix. Okay. But before we kind of launch into the specifics of truss elements, I want to kind of remind you of this whole process, because this whole process is we're going to be following the same thing by hand, or for every single element type. It's just that the only thing that's going to be different in between each of our different element types is step one. Okay. But once you're done with step one, then the rest of the problems follow the exact same process, right? And so we'll do a few examples today that kind of illustrate that concept. All right, so are there any questions on this? This is kind of just a recap from last week. Okay. All right, and so let's look at a truss element. And so let's do a little bit of a derivation of how we can obtain the element stiffness matrix for a truss. All right. And so a truss element, sometimes we call it a bar, right? Okay. And so usually we give it some slender shape like this, okay? And the thing with truss elements is that they're restricted in terms of deformation, is that they can only either extend, and so they can either only get longer or compress or get shorter, okay? And so their deformation modes are kind of limited to just this direction, okay? And so putting it in terms of a kind of cylindrical coordinates, we say that the deformation is limited to just axial deformation, okay? All right. And so just like we did for the spring, we're gonna label both ends of the truss element, and so we'll call the left side node 1, and we'll call the right side node 2, okay? And let's say that we're pulling on this truss with an equal and opposite force in both directions. Okay, and so let's say that we have a tensile force T applied on both the nodes. Okay. In addition to that, we know the geometry of the truss element. Okay, and so we have a length L. We also know the Young's modulus, and so the Young's modulus is going to be given by the symbol E. And we also know the cross-sectional area, which we're going to give the symbol A. Okay. And so for now, we're not going to consider the effects of different cross-sectional shapes. We're just going to kind of lump it together with just a single cross-sectional area A. Okay. All right. And so for a very simple structure like this, where we're just loading it in the axial direction, we have a very simple stress-strain relationship. Okay. And we're going to assume that we have linear elasticity here, right? So, just like we've been doing with static structural, we have just the simple stress is equal to Young's modulus times the strain. Okay, so we have the very standard kind of Hooke's law for a linear isotropic material. Okay. And so let's use this expression as kind of the basis on which we can derive our element stiffness matrix. Okay. Okay. All right. And so let's look at each of the terms in this equation, and let's try to put things in terms of what we see above, right? And so let's start with the stress, because the stress is fairly simple, right? And we know stress is going to be some kind of force divided by an area, right? Right. That's just the straight up units for stress. Okay. And so if we look at our figure above, let's kind of form an expression for the stress according to the information that we have, right? And so let's start with the force. And so the only force that we have that we can see in this figure is the tensile force T, right? So let's go ahead and replace F with T. And we're also given the cross-sectional area. And so let's go ahead and divide that by A as well, okay? And so let's go ahead and plug that in for sigma, okay? And so now we have an expression for sigma in terms of the variables that we've been given. All right. And so on the other side of the equal sign, we have the Young's modulus E, right? And so that's already given to us. And so since we already know the Young's modulus, we can go ahead and leave that alone, okay? And so now let's work on the strain, epsilon, okay? Right, and so we know, the mathematical expression for strain is the relative change in length of the bar divided by its original length, right? Or if you want to put this in terms of derivatives, it would be du dx, right? Where u would be the deformation of the rod, okay? But that definition is not that useful to us, and so we're going to stick with just delta L over L, okay? All right. And so one thing I forgot to label in this figure was that, just like we know for the springs, we're going to also know the displacements of the nodes, okay? And so we're going to say that for node 2, since we're pulling on the rod, and it's going to displace to the right with a with the magnitude U2, okay? And then node 1 is going to displace to the left with the magnitude of U1, okay? And so since we know, how the nodes at the ends of the bar displace, right? Then we can use those expressions to plug in for delta L right here, okay? And so for delta L, if we just do simply U2 minus U1, okay, then we get this entire strain expression equal to U2 minus U1 divided by L, okay? And then we'll have a good expression for the strain as well, okay? And so now that we have a good expression for the stress in terms of the given variables, and we have an expression for the strain in terms of the given variables, we can go ahead and put all this together, and then we can kind of see what we got. Okay. All right. Any questions on this?
Yeah, just for clarification, the U in this case is still deformation.
Yeah, U is deformation. Yeah. Okay, and so let's go ahead and plug in all those expressions, and then let's see what we get. Okay, and so on the left side of the equal sign, we have the stress, which was T over A, right? And on the right side, we have E times U2 minus U1 divided by L. U1 here is assumed to be going to the left, and so U1 is negative. Yeah. Mm-hmm. And so I'm going to manipulate this a little bit. And so I'm going to take this A, I'm going to multiply both sides by it. Okay. And then I'm just going to, just move this L underneath this E right here. So it's not changing anything. I'm just kind of moving the terms around. Okay. And so if we do that, we get T is equal to EA over L times U2 minus U1. Okay. And this is a good point where we can box the equations. And so the reason I'm boxing this is because this kind of gets us into a similar position as our spring equations, right? And so remember the way that we kind of manipulated the spring Hooke's law was we got the Hooke's law into an expression where we have on one side of the equal sign we have force, right? Okay. Is equal to is equal to, on the right-hand side, we have an expression that that states the nodal deformations, okay? And so that's what we have there. And so we have U2 minus U1, actually in the exact same form that we had for the springs, okay? And then in addition to that, we have another expression here that represents the stiffness of the system, okay? And so for our spring, you know, actually, if you kind of look back in your notes, you can see that this equation here is exactly the same as the spring one, except the only difference is that, you know, for the spring, we had the spring constant K right here, okay? But for a truss element, you know, a truss element doesn't have a spring constant. What we have instead is a combination of the material and geometric properties of the truss, okay? And so we have the product of E times A divided by L, okay? And so what we can say is that this expression right here, this E over L, we can say that this is kind of like the effective spring constant of our truss, okay? Truss element. Okay. Right. And so, you know, since this equation right here takes a very similar form as our spring equations that what we covered, you know, last week, what we can argue or what we can say is that then our truss equation should take our truss element stiffness matrix should look very similar to our spring one. Okay. 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 And so to kind of convince you further, you know, let me go ahead and kind of generalize the truss element. Okay. Right. And so if we draw our truss element again, but instead of saying we have a force of T on both sides, let's write it as a general F1 and F2 on both sides, okay? With the accompanying displacements, okay? So we have U2, U1, okay? And then, you know, let's write expressions for what F1 and F2 should be according to this equation up here, right? And then use those two equations as bases for our element stiffness matrix, okay? Right, so just literally exactly the same thing as we did for the spring, except now we're doing it for the truss. Okay. All right. Any questions on this? Okay. All right. So let's go ahead and write out what those expressions should be. Okay. All right. And so in order to have equilibrium, in order for the truss element to be in equilibrium, F1 here has to equal to minus T, right? And F2 has to equal to T, right? And so what this tells us is that F1 is equal to AE minus AE over L times U2 minus U1 And F2 is equal to AE divided by L times U2 minus U1. Right? And so let's go ahead and put this in matrix form, right? Because remember the general form for the element stiffness matrix for an axial element looks like the following. Right? And so if we use the two equations up above to form this linear system, what we get is F2 or F1, sorry, F1 should be on top. I don't know what I'm doing here. Right, so F1, F2, U1, U2. Sorry about that. Right, so we have F1, F2. Okay. Using the equations that we have above, we have positive AE over L minus AE over L minus AE over L and AE divided by L. Okay. Did it again. Times U1, U2. Okay. And so here is our element, our full kind of element system. And this matrix right here, this is our element stiffness matrix for a truss. Okay. And so structurally, you know, it looks very similar to the spring one, right? It's just the only difference here is that instead of a single spring constant K, what we have instead is our effective spring constant AE divided by L. Okay. But this makes a lot of sense, right? So for a spring, you know, if we look at how a spring deforms, you can only stretch a spring and you can only compress it, right? You know, at least in terms of the equations that we have, right? And so for a truss bar, you know, we assume the deformation takes place in the same directions, right? And so the element stiffness matrix should look very similar, but of course the properties are going to be different because you know, we don't have a spring constant for a truss. Okay. All right. And so now that we have the element stiffness matrix for a truss, we can now start to do some example problems with it to see how it, you know, factors into our calculations. All right. Any questions on this before we do an example? Okay. All right. So let's do an example real quick. All right, and so in this example, let's say that we have a 3-bar assemblage. Okay. And so that's 1 bar, that's another bar, that's another bar. Okay. And so we have 3 truss elements kind of in a row like that. Okay. We'll call this element A, call this element B, element C. Okay. I'm using lowercase letters here to not confuse you with the cross-sectional area A. Okay. All right. And so let's say that the Young's moduli for elements A and B, let's say that the Young's moduli for this one are 30 times 10 to the 6 psi. Okay. Whereas the Young's modulus for element C, this is 15 times 10 to the 6 psi. Okay. And so we have a different Young's modulus. And so basically what we're saying is that element C here is made of a different material than elements A and B. Okay. And element C here has a bigger area too. And so if we look at the cross-sectional areas of A and the cross-sectional area for B, we say that these are the same. And so these are the cross-sectional area is 1 inch square, whereas the cross-sectional area for C is 4 inch square. Okay. And so let's say that the length of all the elements is the same, and the lengths are going to be 30 inches. And so in between the two walls right here, we have a total of 90 inches. So you have 3 times 3 elements there. All right. So I'm going to go ahead and label the nodes. Right. So I'm just going to go from left to right, label them nodes 1, 2, 3, and 4. Okay. And you can see from this image right here, because nodes 1 and 4 are kind of attached to a wall, we're going to assume those are fixed. Okay. All right, and so that's the setup for the problem. And so what we're going to do is we're going to use the direct stiffness method here in order to solve for the deformations of nodes 2 and 3. Oh, one more piece of information. And so we actually, because right now in this current configuration, we're not going to get anything interesting because we need a load. Okay. And so let's say that we're applying a rightward load on node 2. And the magnitude of that load is going to be 3,000 pounds. And so this is going to be a load on node number 2 right there. Okay. All right. So quite a bit of information in the setup, but you know, just like we did for springs, we're just going to follow our usual process. Okay. All right, and so step 1 for these problems, you know, just like we talked about at the beginning of class today, is to form the element stiffness matrices for all the elements. Okay. All right, and so to kind of help with this, let's go ahead and just pre-compute AE over L, okay? And so let's do this for element A first, right? And so AE over L for element A, we're going to take the cross-sectional area for element A, which is 1 inch square. Okay. Multiply that by the Young's modulus, which is 30 times 10 to the 6 psi. Okay. And then we're going to divide by the length. And so the length here is 30 inches. Okay. And so, you know, before I compute this, you know, I just want to make a comment just to be careful with your units here. Okay. For this example here, all the units are the same. And so we have all of our lengths are in inches and all of our forces are in pounds. And so, you know, we don't have to do any conversions here. But when you're doing, you know, homework problems or kind of other problems, make sure that when you're computing these, everything is in consistent amount of units. And so for here, you know, we don't have to worry about it because we're all we're all kind of kosher in all of our units here. But you know, just be careful. Okay. All right. And so we perform this arithmetic. You can see those 30s cancel out. And so all we're left with is 10 to the 6, okay? And so in terms of units, you know, the inch square here is going to cancel out with the pounds per inch square for PSI, okay? And then all we're left with is pound per inch. Okay. Okay. And so that's going to be the effective spring constant for element A. It's also going to be the one for element B as well, because B is identical. Yeah.
I kind of have a question about all these methods just
Sure.
in general.
Mhm.
When ANSYS does this, like obviously it's not doing this, but it has shapes like the tetrahedrons and all those. So is it actually filling in values like Young's modulus
Mhm.
and length and stuff like that?
Oh, yeah, yeah. Maybe not length, because we have
Well, I
3D
just mean
elements.
like actual value.
Oh, yeah, yeah, yeah.
Okay.
So for each element, I can give you a little bit of a preview. So for each element, it knows its material properties, of course. So it has the Young's modulus and Poisson's ratio. It knows
So
the
it's forming the stiffness matrix based off those values.
exactly. Yeah, yeah. So for 3D elements, you're going to have, instead of the length, you're going to have the volume of the element instead.
Yeah.
And so the volume is going to make a big contribution, and also kind of the relative positions of each of the coordinates of the
Yeah,
of the
because I was just
element.
having a hard time imagining this for ANSYS.
Oh, yeah, yeah.
Yeah.
Yeah, so for ANSYS, yeah, the biggest complexity in ANSYS is how this is formed for a 3D element versus a 1D element. And so for 3D, you have a lot more geometrical parameters for that one. Yeah. Mhm.
Just kind of like to expand on that. So then for our cases, just to simplify things, we're focusing on 1D orientation.
Correct. Yeah. Yeah. And so we'll do 1D and we'll introduce 2D a little bit today with truss and beams. But we're not going to go beyond that, because beyond that, the math actually gets actually really crazy. So there's actually another set of lecture notes after beams called frame equations, which are 2D elements, but but the math for that gets really crazy. So for these ones, they're not so bad because the element stiffness matrix is 2 by 2. But for the frame elements, the element stiffness matrices actually get to be 6 by 6, 6 by 6 matrices. And if you have a system with, like, say, even something modest, like 3 or 4 different frame elements, you're talking 3 or 4 different 6 by 6 matrices, and you're computing all 36 values of those matrices, and they don't work out as cleanly as this one too. And so I got a lot of complaints. I'll leave it at that. And so we're kind of stopping after beams, because after that the math kind of gets a little bit ridiculous. Okay. And so this is going to be the effective spring constant for element B too, right? So this can be AE over L for element B. Okay. And so the only thing we have left is just to compute it for element C, and then we can start to fill in the element stiffness matrices for that. Okay. All right. Any other questions on this before I turn the page? Okay. All right. So let's go ahead and compute AE over L for element C. Okay. And so for element C, the cross-sectional area for that was 4-inch square. Okay. Young's modulus for element C was 15 times 10 to the 6 psi. Okay. And the length for element C is the same as the other two elements, which is 30 inches. Okay. And so if we perform this arithmetic, this is going to cancel out there. Then what we get is 2 times 10 to the 6 pounds per inch. All right. And so now that we have the effective spring constants, we can go ahead and compute the element stiffness matrices. Okay. And so I use the symbol K with the superscript to denote the element stiffness matrices. Okay. And to denote that they're matrices, I'll put an underline underneath. Okay. And so since elements A and B have the same, actually, let me do this, because even though they have the same values, they have different, they act on different nodes. So let me actually do each of them individually just to make it clear. Right. And so for the element stiffness matrix for element A, we have the effective spring constant, which is 10 to the 6, minus 10 to the 6, minus 10 to the 6, 10 to the 6. Okay. And then we have to list out which nodes that element A acts on. And element A is going to act on nodes 1 and 2. So we need to make sure we specify that in our matrix, just so that we know where to put them. Okay. Okay. For element B, we have the same values in our matrix, but they're going to be acting on nodes 2 and 3 instead. Okay. And then the element stiffness matrix for element C is going to be 2 times 10 to the 6, minus 2 times 10 to the 6, minus 2 times 10 to the 6, and then 2 times 10 to the 6. Okay. And then for element C, we're acting on nodes 3 and nodes 4. Okay. All right. And so now that we have the element stiffness matrices for all these elements, we can go ahead and assemble them into one system. So next step is assembly. Okay. All right. Any questions on how we got these values for the element stiffness matrices? Okay. All right, so let's go ahead and put them into the one global system. And so our global system here is going to be 4 by 4 because we have four nodes total in our system. Okay. And let me go ahead and label the columns. Okay. And then on the right side, we have all of our forcings, okay, which we'll fill in later when we do our boundary conditions, but we're going to leave them alone for now. All right, so just like we did with the spring problems, let's go ahead and mark out the regions in our global linear system where we're going to insert our element stiffness matrices. Okay. Okay. And so element A, we know acts on nodes 1 and 2, and so we're going to go ahead and box out those regions in the global linear system. Okay. Okay. And so that's going to be the region for element A. Okay. Element B is acting on nodes 2 and 3, and so we're going to go ahead and box that region in our both the 2 and 3 columns and the 2 and 3 rows. Okay. And so that's going to be this region right here. Okay. And then finally, we have element C. Okay. And so element C works on nodes 3 and 4. Okay. And so that region is going to be this one right here. All right, and so let's go ahead and fill in the values. Let me go ahead and fill in the rest of what's not boxed with zeros. Okay. Okay. All right. And so let's start with element A first. So element A is 10 to the 6th, minus 10 to the 6th, 10 to the 6th, and then, or minus 10 to the 6th, and then 10 to the 6th. Okay. Next, we have element B. And so first we have this overlapping part right here. And so remember, whenever you have overlap between two different elements, then you're just going to add together their values. Okay. Okay. And then finally, we have the contributions from element C. Okay. And so let me go ahead and just perform the addition in the overlapping regions. Okay. Right, and so if we perform that addition there, we get 2 times 10 to the 6. And then for this region right here, we have 3 times 10 to the 6. Okay. All right. And so that's how we assemble our global linear system. Okay. All right. And so now that we have this, our next step is going to be to apply boundary conditions. Okay. And so for our boundary conditions, we have 3 in this case. Okay. And so the first boundary condition is a fixed constraint on node 1. Okay. The next boundary condition is a fixed constraint on node 4. And then our last boundary condition is a load of 3,000 pounds applied on node 2. Okay. And so let's go ahead and apply all of these boundary conditions. All right, so let's start with the constraints, right? And so remember, for the constraint type boundary conditions, we go to that row in the matrix, and then we replace that row with a 1 on the diagonal and then zeros on the off diagonal, right? And so let's start with node 1, okay? And so node 1, we're going to go to the row in the matrix that corresponds to row 1. We're going to erase all of the terms there, okay? And I'll erase these two just for illustration's sake. Okay. We're going to put a 1 on the main diagonal, right? And then we're going to place everything else with zeros. Okay. And then we're going to do the same thing for node 4. Okay. And so node 4, we're going to have 0, 0, 0, 1. And then a 0 on the right-hand side, okay? And so those are our constraint boundary conditions on the two ends of our truss, okay? Next, we have our load type boundary condition, which is applied on node 2, okay? And then we're going to apply our 3,000 pound load right there. And so we're just going to drop that right in, okay? And then the last thing, since we don't have any boundary condition on node 3, so we don't have any load or constraint, then we just replace F3 with 0. Okay. All right. And so now that we have this linear system right here, we have our left-hand side matrix, and we have our right-hand side forcing vector. We can go ahead and solve this. And I think for me, I solved this in MATLAB. Because even doing like a 4x4 system like this can be challenging. Although because we have two fixed constraints, we end up with just 2 equations and 2 unknowns. But even that's annoying to do by hand too. And so I think the easiest thing is just kind of plug this into MATLAB. Okay. All right. Any questions on what we did here before we jump into the solution? Okay. All right. So let's go ahead and look at the solution. And so if we plug these all of these parameters into MATLAB, then what we get is U1 is equal to 0, U2 is equal to 0.0018 inches, okay. U3 is equal to 0.0006 inches, and U4 is equal to 0 inches. And there is our solution. And so what this solution says is that the node 2 is going to deform the most. And so node 2 is going to deform to the right with a magnitude of 0.0018 inches. And so not that much, but it is measurable. Okay. And then node 3 is going to displace to the right with a magnitude of 0.0006 inches. Okay. All right. And so that's your solution. And so one more thing that we can do with this solution. Oh, question.
Oh, I was just gonna say, so in ANSYS, it solves for the deformation and then you set against the stresses
Exactly.
from the deformation.
Yes, yeah, and actually, I'm going to show you how that's usually done in practice. And so for this one, we're not going to be able to solve for stresses, but what we can solve for are the reaction forces at all the nodes, right? And so that's one thing that's usually solved for second. Right, and so just so just like it was mentioned, the first thing that ANSYS always solves for is going to be your deformations, and so that's what we got there, okay? And then from those deformations, everything else is solved for, right? And so for ANSYS, that'll be like your structural stresses, but for this particular problem, we can use this result to find out what the reaction forces are at each of the nodes. Okay? And so for this particular case, because we have two fixed constraints, and so we have a fixed constraint at node 1 and a fixed constraint at node 2. And so, we're going to have reaction forces at these nodes. And what those are basically the forces that the walls, or kind of the structures that we're fixing this to, those are the forces that are being applied onto this, onto this 3-bar assemblage that keeps the overall structure in static equilibrium, okay? Okay. And so to find these reaction forces, we're going to take our solution and plug it back into our global system. Okay. But we're not going to plug it into the global linear system that we have previously right here, right? And so the global linear system that we're going to plug it into is going to be the one that we use before we apply boundary conditions. Okay. All right. And so for this, system right here, if you look back in the notes, before we apply the boundary conditions, our global linear system looked like this. Okay. Right. And so before we applied the boundary conditions, we had, our global linear system look like this, right? Previously, we couldn't solve this equation for U1, U2, U3, U4 because, this system was singular. If we try to invert this matrix, we would just give an error. But we don't need to invert it this time. And so, because now that we've already solved for the solution, we already know what these values are, right? And so we can just plug in our values into this and then just perform the matrix vector multiplication in order to solve for, F1, F2, F3, F4. Okay. And so if you do this, what you're going to get is F1 is equal to minus 1,800 pounds. F2 is going to equal to 3,000 pounds. F3 is going to equal to 0 pounds. And F4 is going to be equal to minus 1,200 pounds. Right. And so let's look at the magnitudes of these values here and kind of see if they make sense relative to our structure, right? And so the first thing that should jump out to you is F2, right? So F2 here is 3,000 pounds, which is exactly the value of the load that we're applying there, right? And so when we compute the reaction forces at these nodes, we should get the exact values for the, for those, for wherever we're applying load. So that makes sense, okay? And so the other two areas that should jump out to you are F1 and F4, which is, this is where we had our fixed constraints in our situation, okay? And we have reaction forces here that are in the negative direction, okay? And so these are going to cancel out the 3,000 pounds for F2, okay? And if you add them together, if you add F1 and F4 together, you'll see that we get exactly minus 3,000 pounds, okay? And so if you add all of the reaction forces together as one, you'll see that you'll get 0 pounds overall, okay? And so this is kind of a good way for you to check your answers too, because getting up to the point where you get a finite element answer to a direct stiffness, there's kind of a lot of steps along the way. And so if you want to check your answer just to make sure it makes sense, this is a good way to do it, is to compute your reaction forces and first of all see if they add up to 0 to make sure that you have static equilibrium, and then also just make sure that you have your load values are recaptured, and your only reaction forces are going to be at the places where you have your fixed support. All right. Any questions on this?
Quick question. I'm totally blanked out. Not on this portion, but on the portion of the boundary condition.
Mhm.
So we have 4 unknowns, but 3 boundary conditions.
Yeah. Mhm.
Is that kind of like because of the load constraint? I don't know. I think I'm like mentally like I don't know, but
Yeah. So you don't need the same number of boundary conditions as unknowns, because all the equations for your unknowns are tackled by the element stiffness matrices. And so just by the existence of this whole system right here, we already have our 4 equations for our 4 unknowns. And so what the boundary conditions are going to do is that they're just going to modify the system just to make it solvable. Because if you look at the state of the global linear system before we applied boundary conditions, right? And if you kind of drew a line like this, right? You can see that our matrix here is symmetric, right? And so we have kind of the same things above and below. And so if you try to basically solve this linear system as it is, you're not going to find an answer, because it's basically a singular matrix. And so if you try to invert it, then you're going to get nothing. And so what the boundary conditions do is that they modify the global linear system so that you can actually solve for a unique solution. Yeah. And so the number of boundary conditions is not correlated with the number of unknowns at all. It's just it just makes sure that you can get a unique finite element solution from the linear system. Okay.
So it's kind of okay.
Mm-hmm. Yep. Mm-hmm. All right. Any other questions on this example here? Okay. All right. And so that's trusses in 1D. And so, that's not too different from our springs. And so, for the last 15 minutes of class today, I'm going to introduce the concept of doing both truss and spring problems in 2D. Okay. And so I want to make a distinction here, because we're not going to move on to 2D elements. And so we're not going to have triangles or quadrilaterals here. The only thing that we're going to do is that instead of having a truss element that's just going in one direction like this, now we're going to open it up so that we can have truss elements that skew right? And so it might be going slanted upwards like that, and we might have multiple truss elements that kind of come together like this, okay? And so our elements are still going to be are still going to be 1D elements. It's just that we're going to be moving them around in 2D space now, okay? Okay. So elements themselves are still 1D, but can all right. And what you'll see is that this kind of introduces a whole new set of complications. And so we're not going to move on to 3D because when you move on to 3D, things get even more complicated. But I think it doesn't have as much value. And so the jump from 1D to 2D, I think, illustrates a lot of really core concepts in finite elements. But from going from 2D to 3D, we don't really gain nearly as much. And so we're just going to stop at 2D. Okay. All right. And so to motivate this, or to kind of set us up for this, I want to introduce you to the concept of what I call the local coordinate system versus the stationary coordinate system. Okay. All right, so let's start with the local coordinate system. Okay. And so the local coordinate system is basically our coordinates for X and Y that are local to a particular truss element. Okay. Okay. And so let's say that we have a truss element. Okay. And then, let's say that we've rotated it upwards like this. Okay. And so now the new configuration for the truss element looks like this, right? Because we've rotated it upwards. Okay. And let's say that we've rotated it upwards with an angle of theta. Okay. Right. And so, before the element was rotated, we had our XY coordinate systems that look like this, right? So pretty standard. And so X is the horizontal direction and Y is the vertical one. Okay. But once we rotate it, we're going to find it more convenient to say that, along with the element rotating up with an angle of theta, if we rotate the coordinate system along with theta so that, the X axis kind of stays parallel to the element itself, right? Okay. We're going to find that this coordinate system is really convenient for us because remember the restriction that we have for truss elements, where truss elements can only extend and compress, right? And so the only deformation is going to be along the axis of the element itself, right? And so if we have a coordinate system that represents that, that's going to be really convenient because then what we can say, and just to make these different, I'll give them a hat, okay? Right. And so when we're forming the element stiffness matrix for this rotated element, if we do it in terms of the local coordinates, then we can say that the deformation is going to be limited to the X hat direction, okay? Okay. Because the X hat direction did not defines, tension and compression for that element. Okay. And that's going to be really convenient because what you'll see is that, if we have our element system localized to the element like that, we can actually use the exact same truss element stiffness matrix we've been using before, except that instead of doing it in classical just X and Y just by itself, it's going to be between the X hat and the Y hat direction. And that's going to be really key. right, and so the local coordinate system, I'll give those a hat. And so, I'll put a hat like that, okay? All right, and so the other coordinate system that I want you to keep in mind is the station, what I call the stationary coordinate system. So sometimes sometimes in the literature you'll see this called the global coordinate system, but I don't want to use the word global because we're using global for something else already. And so I'm going to call them the stationary coordinate system because they're not going to move. Okay. And so this is a coordinate system that's essentially going to serve as our reference point, right? And so it's going to be basically our classical X and classical Y. Okay. And so, as we kind of develop these kind of 2D elements, we need something to kind of, refer back to, right? And the stationary coordinate system is going to be that, okay? Because, what we'll see is that, we're going to have, assemblies of lots of these different truss elements, right? And they're all going to be oriented a different way, right? And so let's say that we have another truss element, maybe it's vertically upwards, okay? And let's say that we have another one that maybe is, rotated downwards like this, okay? And so they're all going to have an angle that's associated with that, right? And so let's say that this is rotated by an angle theta. And let's say that this is rotated all the way around by an angle theta orange, okay? Right, theta, we have theta red, theta blue, theta orange, okay? And so, we can't just keep making local coordinate systems for all of these different elements. Or actually, no, we can, and in fact, we're going to do that. But we need something to kind of relate it back to, just so that we can kind of systematically compare their deformations to each other, right? And so that's the role of the stationary coordinate system, to kind of stay fixed, in space, and then we're going to basically define all the other transformations based on the stationary coordinate system, okay? And so the stationary coordinate system doesn't have a hat, okay? And so whenever I give you an X or a Y or something without a hat, then it's for the stationary coordinate system. Okay. Okay. And so the key to our 2D problems, and it's you kind of already see it implied in the image I have below, is our key here is going to be the relationship between the local coordinate system for a particular element and the stationary one. Okay. And the way that we're going to relate them, because we're dealing with just 1D elements here, is through a rotation, okay? I'll write that on the next page because I remember. Okay. Any questions on this so far? Okay. All right. And so relationship between local stationary coordinate systems All right. And so let's say that we have stationary coordinates, classical X and Y, just like that, okay? And so the local coordinates, so let's say that we have an element that's oriented with an angle theta, you know, it might look something like this. Where this is going to be our angle theta that we're rotating. Okay. All right. And so the key to our transformation here is, you know, is going to be able to take a vector. And so let's say that we have a vector u, okay? This u is actually the same in both images here, okay? Okay. The difference is that if we're defining u, or if we're defining the components of u, the values of the components of u are going to be different depending on which coordinate system that we're looking at. Okay. But the vector u itself is the same. And so, you know, whether we represent it in the stationary coordinates or we represent it in the local coordinates, u is going to be exactly the same. Okay. And so in other words, you know, if we use standard unit vectors, and so if we say that the unit vector in the stationary x direction is I, and the unit vector in the stationary y direction is j, and the unit vector in the stationary local x, we'll call this I hat. Okay. And the unit vector in the local y direction, we'll call that j hat. Okay. What we should have is that the components of the vector in the stationary coordinates, okay. And so we have uxi plus uj or uyj, okay. This should be equal to the same vector, but just different component representations. Okay. And so we should have this whole thing equal to ux hat times I hat plus uy hat times j hat. Okay. Okay. All right, so this equality should hold because the vector u is exactly the same. It's just that we're kind of defining it in a little bit of a different way. Okay. It's like that whole, it's like that romantic saying, right? So a rose called by any other name is still a rose, right? So u defined by any other coordinate system is still u, right? Poetic, but also not interesting and not as interesting as probably Shakespeare, but you know, we should have this equality hold because, you know, u is still the same. Okay. But this expression here is a little bit annoying because we have kind of a little bit too many values going on. Okay. And so what we're going to do, and I think I'll start it today, but we'll definitely pick this up on Thursday, is that we want to find representations for these unit vectors in terms of just one system. Okay. Okay. And so we're going to basically form a transformation between the i's and the j's in one coordinate system and the other one using trigonometry. Okay. All right. Any questions on this?
Is that supposed to be I plus j or I and j?
Oh, I and j. Yes.
Okay.
Okay. So I think we are just about out of time, and so yeah. So I think if I go any more, I think it would take a little bit too long. And so let's stop it here, and then we'll pick this right up on Thursday, where we'll see how we perform the transformation. And eventually we're going to get to what's called the transformation matrix. And then we're going to use that to do our truss problems in 2D. Okay. All right. And so thank you guys for coming today. Hope you guys enjoy the rest of your evening. Remember, the due dates for activity 4 and the midterm project are pushed back. And so I'm going to go update the Canvas site right now, because this is kind of the first chance I've had today with any free time. And so, hopefully that gives you a bit more freedom. Right. So have a great day. I'll see you guys on Thursday.
Thanks, Dr. Tran. We'll see you later.
Thanks, Steven. See you later.
Thanks again. See you.
Yep.
Thank you, Professor. Have a nice night.
Wanted to show you the activity to see.
Okay.
So with the additional.
Yep.
Yeah. I got this was the definition.
Yep.
And then, was over.
Yep.
And then for the second time, the strain and change.
Yeah.
Okay.
So this is a lot more realistic. Normally you have a grid like this, you're going to start on the bottom. Right. So yeah, that should be it.
And then the displacement, that's just to be, that the difference from that versus fixed means that it's not moving in a certain direction, right? But it can still perform.
Yes, yeah. And so you're basically with the displacement constraint, you're basically. Thanks, guys. And so we're basically preventing the bridge from displacing in the y direction, which is this direction. In this model, it's the actual vertical direction.
Okay.
But it can still kind of move in an x and z direction.
Okay.
And so the reason I did that is because I was a little bit worried. That the bridge might be a little bit too stiff in 2 fixed conditions, but in reality, it's actually fine. So it could have been 2 fixed conditions there. But it was also kind of a good chance to show you guys that you can do a roll with stuff like that too.
Okay. And then for one of the solid elements, is that kind of what it looks like? It's all.
Yeah. So for the solid elements, I would say about half the people are not going to be able to complete it just because it gets too expensive. But if you do complete it, it does look like that.
Okay.
It is weird though, because I don't get the same.
I don't get why it's.
Yeah, because
there.
Yeah, because I got the same thing. So I was playing basically just a weight mode on top, but it seems like it's kind of just tilting one way, which doesn't make sense because it's a symmetric mode. And so I think what's happening, and I didn't get a chance to really examine this, but I think some of the connections in the solid element mesh are not properly defined. Because this CAD model is not the cleanest in the world. And so I think some parts just weren't close enough to each other to actually form a good contact. And so I think that's what's happening. That some parts are bonded, but some are not. And so that's why you get this kind of weird asymmetric displacement distribution.
Okay.
When you shoot. But yeah, don't worry about it. If you're able to run it, great. But if not, then then don't worry about it. Since you have it, just comment on it.
And then the one other question I had, I was trying to start the midterm project.
Yep.
I've been looking at like all the different. I wanted to go with the turbine blade.
Yep.
I was looking at all the different forces. So if say this is like a jet engine turbine, we have the wind going this way, right? You have the different wind velocity vectors.
Yep.
Would I just apply it along here, or would I have to include like the lift force as well as drag and apply different forces, or would the wind force, would that already just induce the drag and the.
You can do both actually. I think that'd be interesting. And so if you have, a force in this direction, that would be like a drag force, like you said. And so that would, I think, make the most sense here.
So is the wind blowing? I was getting confused because would be like your foil.
Yeah.
But would the wind be, which direction would it be getting blown, in this way or?
So for my original intent was for this to be like a turbine blade. So like there'd be like a lot of these kind of connected to each other, and they'd all be kind of spinning together like that. And so originally I imagined the wind kind of pushing in this direction cause a rotation in that direction. But you can interpret this as like an airflow too, I think, because it has that shape too, and that's perfectly fine. So these geometries are kind of just almost like a canvas, and so you kind of do whatever situation you want. And so I think using it as like an airflow, it makes a lot of sense.
So it'd be cool if I did wind this way, lift this way, and then drag that way.
So this would kind of already be the drag.
Or the drag, yeah.
And so yeah, I think doing lift that way, drag that way. I think
I think that'd be really cool.
Okay, cool. Thank you.
Yep. Just a quick question. I think I did just kind of wanted to like think about this more. This transformation matrix, is this sometimes referred to the rotation matrix?
Yes, yes.
Okay.
So rotation is a little bit more specific. So transformation is kind of a more general term where you can do both rotation and like a linear transformation. But for our case, we're just gonna be doing that. But I'm going to call it transformation matrix, so that's kind of the name for the matrix for it. But transformation in general can be rotation and transformation.
But just in our case, it's just focus on rotation.
Yeah.
Okay. Okay, thank you.
Yeah.
Hey, Professor.
Hey, what's up?
Have a question on problem 7 on my simulation.
Okay. Mhm.
I think